Hi guys, Mr. Janowski here. So this is another one from the Chapter 9 study guide. This is problem 7. So we're going to start a game of pinball. I don't know if you're all familiar with pinball, but there's the little plunger thing you pull back. It's a spring-loaded device. So we're going to pull back the spring 0.115 meters, so 11 and a half centimeters. The spring constant is 1575 newtons per meter. The 4.12 kilogram ball shoots up the slope through a vertical height of 0.325 meters. What is the ball's velocity when it reaches the top of the slope? And there's our answer. So this is going to be a conservation of energy problem, and we're going to do it with the big strategy we learned. So let's get started. Now for the loud part, where I flip my Chromebook from being a Chromebook into being a tablet. That wasn't so bad. All right. I don't know I could even do that. All right, so here we go. So as usual, we start off with step huh. What are we trying to solve for, and what units do we expect it to have? So the last sentence, what is the ball's velocity when it reaches the top of the slope? So we're looking for the final velocity of the ball. So V final equals question mark, and the units of velocity, as always, meters per second. So now we do step 1, and all year long, step 1 is make a sketch. But if it's a conservation law problem, which is what this is a conservation of energy problem, you're actually going to make 2 sketches. So first you want an initial sketch that shows what's going on at the beginning. That looks sloppy. Believe me, that is the word initial somehow. Dot that I, T. Okay, that's initial. So what's happening at the beginning? Well, there's a slope. Pinball's, kind of like a ramp. So here's our little plunger thing. And to start a game of pinball, you pull back on the little spring-loaded thing. So when it says you pull the spring back 0.115 meters, that's this distance here. So this is where the spring would be before you pull it back. So that is X initial, our initial compression, and that is 0.115 meters. I'm going to not write the mass because this is getting a little sloppy. Sorry, I'm just going to always complain about the stylus because the stylus in this thing is pretty crappy. Our final sketch. So what's going on at the end of this? So there's our slope. The spring's still there. Draw it up to there. But we've released it. There's no more tension in the spring. It's not compressed or extended anymore. So we're back to its equilibrium point. So what that means is X final is going to be 0 meters. And where's the ball at this point? The ball is at the top. It's moving. So you can imagine it's going to go up here and then swing into the table over this way maybe. It is moving, so we're giving it speed lines. And the thing we're trying to figure out is what's the final velocity. So there's step 1. Step 2 in an energy problem is write the law of conservation of energy. So hopefully I can squeeze it all in on this page. So the law of conservation of energy is sigma E initial plus sigma work external equals sigma E final. So the sum of your initial energy plus the sum of your external work is going to equal the sum of your final energy. So we're not going to deal with friction or air resistance or anything like that. So there's no external work being done here, so that's just going to be 0. So now we go to this sigma E initial term. So what you do is you look at your initial sketch and you ask yourselves 3 questions. First question, is it moving? So look at the initial sketch. It's not moving. There's no speed lines. So that means there's no initial kinetic energy. Second question, is it at a height greater than 0? It isn't. This thing's going to change height in this problem. And at the beginning, it's at the lower height, so we're going to call that 0. Just now realized I forgot to deal with the heights when I was making my sketches. Oh well. But our initial height, 0 meters. So it wasn't at a height greater than 0. Therefore, there was no initial GPE, gravitational potential energy. And the last question, is there a spring that is extended or compressed? There sure is. So our spring is initially compressed. So that means there's energy in the spring. So we do have initial elastic potential energy. So EPE initial, that's going to be something. Plus sigma, sorry, that was a sigma. Plus sigma work external, well, that was 0, equals the sigma E final. So now we've got to look at this term. And to do that, we look at our final sketch. And we ask the same 3 questions. Is it moving? It is moving. We do have the speed lines here. So that means there is final kinetic energy. Is it at a height greater than 0? Yes, it is. I wrote it in the problem. I forgot to add it to the sketch. But our final height, H final, is 0.325 meters. So that means that height there is 0.325 meters above the height we started at. So we're at a height greater than 0, so that means there is GPE final. And the last question, is there a spring that is extended or compressed? Well, there's still a spring, but it's not extended or compressed. X final is equal to 0. So that means there's no EPE final. So in this problem, we're going to start with EPE initial, and we're going to end with KE final and GPE final. So let's get a new layer going here. And change colors, because let's go to purple now, because we're doing a new step. So step 3, let me just rewrite what we just had. We had EPE initial equals KE final plus GPE final. Now we turn all the things into the things. So look at all the terms here and then use the little footer at the bottom and replace each term with what it's equal to. So EPE initial, that's going to be 1/2 K X initial squared equals KE final. So that's going to be 1/2 M V final squared All right, I gotta try this one more time. Sorry, my stylus really doesn't like doing things in the middle. Damn it. All right, trust me, that's a 2. Plus GPE final. Well, your formula for GPE is MGH. So this is MGH final. So we've got an expression. It's got a bunch of terms. The term we're looking for again is the final velocity. So we've got to do some algebra to get this guy by itself. So first thing, subtract the MGH final term from both sides. That'll give us, on the left, 1/2 K X initial squared minus MGH final. And this is going to be equal to 1/2 M V final squared. So we've got more algebra to do. Multiply both sides by 2 to get rid of the half. And do this carefully because people like to make this mistake. So when you multiply everything by 2, on the left, that's going to kill that half there. So that's going to become kx initial squared minus, this is the part people forget. We have to multiply the whole left side by 2. So you need to have a 2 show up right here. MGH final. And this is going to equal M v final squared. So convince yourself that that algebra is true. Next thing is I need to get that m away from the right side. So I'm going to divide both sides by m, which just barely fits here. So that'll kill the m on the right side. And watch what happens on the left, because the m doesn't cancel everywhere. This is another mistake people like to make. In your numerator, there's two terms. There's no m in the first term, so you can't just cancel the m's everywhere. Just because it would have canceled in the second term doesn't mean you can just cross it out completely. So let me write that up here. So what would we have? This would give us, I'm going to switch left and right here. V final squared is equal to kx initial squared minus 2 mgh final. All of this over m. And then take the square root of both sides. Just barely fits, which will kill this square root right here. And then we got to go to the numbers. And let me change colors just so, I don't know, we can keep this idea separate from the other one. So I'm going to jump down here, and I'm going to leave out the units because there's no way this will fit on the screen if I try to include them. So big square root. Our number for k, 1575. Let me put that in parentheses. Oop. Parentheses. X initial, which gets squared. Okay, x initial, 0.115 meters squared minus, I just realized I really don't have enough room here, minus, so this is going to look a little sloppy, our mass, 0. You know what, let me just start a new one. So what did we just have there? We had V final is equal to square root of k, x initial squared, minus 2 mgh final, all of this divided by m. All right, so now I'll write it down here, and this time I will include the units because this time it'll fit. So V final is equal to big square root k, 1575 newtons per meter, times x initial squared, so 0. Come on, 115 meters squared, minus 2 times the mass, which is 0.412 kilograms, times g, 9.8 meters per second squared. Anyone else nervous that I'm going to run out of space here? H final, 0.325 meters. Just barely fits. And again, you've got to do all that stuff and then divide it by m, which is 0.412 meters. So it's a lot of work to do in the calculator. Make sure you're doing the entire numerator and then dividing by the denominator and then taking the square root. The order of operations you do is going to be important here. But if you do all that stuff, what you should end up with is V final is 6.65 meters per second. Put a box around it and do step we solved for the right thing. We wanted the final velocity. We have it in units of meters per second, so that makes sense. And then quick bloody cheetah. We have about 6.5 meters per second, so multiply that by 2. That's about 13 miles per hour. That's a reasonable speed for a pinball to go. So we're happy with that. So hopefully that makes sense.